Hello students, welcome back to another lecture on classical mechanics. And in continuation to our previous lecture, especially with the rigid body dynamics and then moment of inertia tensor, we have also seen some introduction to the index notation. So that is quite helpful to write down expressions in index form. And later we will be calling such objects as the tensors. And that introduction would be sufficient enough to deal with the special relativity. And therefore, in today's class, we will start with the special relativity. And in particular, if you are going to start the special relativity, the point that I would like to address in the today's class is to explain what is the main reason for the development of relativity. So, if there is a fire, okay, there should be certain starting point like a sparkle, okay, or like you are starting with a matchbox. That is called sparkling. The initial spark should be there, only then the ignition is there. So in the case of the special relativity, what was that? So what was the strong motivation for the development of relativity? That's the first point that let us discuss. That is one thing that I would like to explain. The second thing is that in general we will be having an opinion that relativity means Albert Einstein. Okay, that's fine. But the point that I would like to tell you is I would like to ask whether the concept of the relativity is introduced by Einstein himself, or whether the concept of relativity was there much earlier. That is the question. So the answer is that the concept of the relativity was there much earlier, even before Newton. Because as far as mechanics is concerned, we are concerned mainly with the Newton and then later with the Albert Einstein. But the point is that the subject of the mechanics is got developed even before Newton, as we know that Galileo is the person. So Galileo is senior to Newton. So he is the person who has developed mechanics. But however, formal equations were not there, but understanding and observations were there. That is first thing before Newton. And before Newton, there is another big person involved in mechanics, and he is the Kepler. So Kepler's laws of planetary motions were discovered much before the Newton's laws. So which means that when the Kepler is writing down his equation, there is no idea about the Newtonian gravity. Okay, you have the Newton's law of gravitation, right? That itself is not known to the Kepler. So that is why I told you that the Kepler's observations, so they are not equations. Kepler's observational astronomy, that is the one that gave you the laws. So similarly, in the case of the Galileo, they are the daily life experience. That means observations. So observation has given ideas about the relativity. So that's what I would like to tell in today's class as a starting point. And therefore, what concept was there at the time of Galileo? That is known as the Galilean Transformation. And once that Galilean transformation is there, people were happy for quite a long time. And then something happened and it gave trouble that the Galilean transformation is not correct and we have to do something. This kind of issues came after some time, and why that issue has come and how it has come. So that is a point that we are going to see in the today's class. And let me therefore write down the first one that we see, that it is the Newton. By the way, don't worry about these years. I'm not going to tell any history, but this is a good information that if you have some numbers, it is better to understand. NLM means I am writing for the Newton's laws of motion sometime in 1687. So I am writing Newton here. I am going to write the Galileo before this. So that you'll be able to realize that Galileo is a senior person to the Newton. So I will write the Galileo now. So Galileo, the point to be noted is that his work and together with the Kepler's work form experimental basis or observational basis for the mechanics. I'll write together with the Kepler also, because Kepler also happens to be before Newton. So I'll write down like that. Kepler during 1571 to 1630. So once this is clear, the next to Newton, the very big work is done by Maxwell. So there was a big gap between Newton and the next important work, and therefore let me therefore write down the important work by the Maxwell, and that was during 1831 to 1879. Okay, that periods are not important for the time being, but however, what is important is when Maxwell's equation came. So Maxwell's equation came into existence in 1685. So roughly, if you see 1685 and the original Newton's NLM means Newton laws of motion, what is the time difference? 1600 to 1800. So you calculate approximately, let us not calculate accurately. That number is something like 200 years. It is easy to remember like that. So for 200 years of time, people were happy about whatever was there with the Newton, and that's all about it. And then with the Galilean relativity. So remember that Galilean relativity is before Newton. So afterwards, what happened is, after Maxwell has given this Maxwell's equation, Lorentz work became very famous, because Lorentz has done quite a bit of work in electromagnetic theory, and in particular Lorentz got the Nobel Prize for that in the electromagnetism in the year 1902. By the way, Nobel Prize means, Nobel Prize itself started sometime at that 1900s. So that is the reason I would like to mention that Galileo, Newton and Maxwell, they didn't get the Nobel Prize. Okay, that doesn't mean that they didn't do work. It's not like that. Nobel Prize itself was not there. The concept of the Nobel Prize itself is not there. So that point I'll to be noted down, and therefore I will better write down that in 1902 he got the Nobel Prize, especially for his work on electromagnetism, Lorentz. Okay, Maxwell is very near to that. You see, 1888, something like that, Maxwell's equation got popular, but at that time the concept of the Nobel Prize itself was not there. Okay, so all these things are over, and then finally Einstein's work was there during the period up to 1955, and then of course the other popular things are, let us forget about that. Let us go back to the Galilean situation, and the development made by the Galileo is what is known as the Galilean relativity. So I'll write down that. So why I am writing that is to emphasize the point that the concept of the relativity was there all the time right from Galileo. So it is known as the Galilean relativity. And then the next relativistic concept has been introduced in a big way by Lorentz. So I'll put an arrow. Let me finish this Galilean, namely the Galilean transformation. I'll write down that. Okay, so now it is clear: Galilean transformation, Lorentz transformation. Okay, all these things are clear. If it is the case, what Einstein did. So now the point is clear, right? The concept of the relativity has been done. So much work is done by Galilean and Lorentz. In that case, what Einstein did, or what was the big input from the Einstein that changed our understanding? So this gives you an overall idea about the interest behind relativity. Okay, so the starting point is always Galilean relativity. Therefore, we need to understand where the trouble came actually. Okay, so therefore, let me put a box or some kind of I'll highlight that after finishing this Maxwell's equation. Okay, whatever I am writing, this technical term I will explain later. I am writing not invariant under GT. I am writing GT is, okay, I will write GT. GT is Galilean transformation. So about the invariance, I will explain as we go along. So the central theme is, what is that? That's why I want to write down LT for Lorentz transformation, GT for Galilean transformation, and then the central theme I would like to highlight that Maxwell's equations are not invariant under Galilean transformation. So that is the highlight. So keeping that in mind, we are going to our understanding would be better that this is the central theme. I'll write down that it is a central theme. So this 5 minutes introduction will give you a clear idea about why the relativity has started in a big way. What is the starting point? I asked what is the sparkle, right? This Maxwell's equation is the starting point. They are not invariant under GT. That is why people started to dig what is wrong with the Galilean transformation. So therefore, I will now write down. Let us start in a mathematical way. Let us understand. Let me therefore write down the principle of relativity. So concept wise it is clear. Okay, so Maxwell's equation gave the trouble, and therefore one has to think over what to do with the transformation. So but if I give only that statement, it is people will not be convinced, and therefore let us do some mathematics. Then only we also can accept and agree and then get convinced that the Maxwell's equations are giving trouble with the invariance. So let me therefore write down what is that meaning. Okay, the statement of the principle of relativity is quite simple, that all the physical laws, okay, all the physical laws must be invariant. But okay, laws means something like equations. Everything is in mathematical form. So physical law means not English statement. Appearance of the equation, that is what I mean to say. Appearance of the equation is very important. That is what I am writing form. They are form invariant. When it will be form invariant is under some coordinate transformation. So if you don't do anything, then nothing will change. Okay, so we have to do something. So that is the coordinate transformation. We are going to do a coordinate transformation and then ask the question, what happens to the original equation? If the original equation remains intact, we say invariant. So what is invariant? Let me put down the meaning of invariant. Invariant means something that does not change. Okay, something that does not change. So if the appearance, what do you mean by not changing? Means equation appearance. It is the appearance of the equation. That is the meaning of form. Form means appearance of the equation. So that is clear. So then the coordinate transformation is physically known as frame of reference. So generally frame of reference by physics people, mathematicians like the word coordinate transformation. So let us therefore see the terminology. So what is the terminology you are going to learn in relativity is the name invariant. That is the main thing that you are going to learn, and covariant in the language of tensors. So invariant means in simple English, covariant means in the language of tensors. That's all. That is the terminology. First point. The second important point about our second terminology is the coordinate transformation. What is the meaning of coordinate transformation? How many varieties are there for the coordinate transformation? So if you can classify, then we will be able to understand better. So let me therefore split it. Okay, I want to write three types of coordinate transformation. Namely, the first one is the easiest one: translation of the coordinate axis. Either you say coordinate axis or you say coordinate system. This is the easiest one or the simplest thing. Then the second and the third variety, I will now write down. The second variety I would like to write down as the rotation. You can also rotate a coordinate, right? That's what I want to write. So I will write down as a rotation of coordinate axis. Coordinate axis or coordinate system, whatever it is, that is the meaning. Rotation of coordinate axis. And the third one is the moving coordinate system. So we can have two different names. Let me write down the simplest word that we can write down: moving coordinate system. There is an alternate name like velocity transformation, but both are same. Okay, so I'm trying to give you similar terms. Moving coordinate system means velocity transformation. That means velocity is involved there. So I will write down what is the meaning under each category. What do you mean by translation of coordinate system? It is just moving a coordinate system. I have a coordinate, simply move it to another place. CS means coordinate system. Okay, just moving a coordinate system to another location. Simply move it. That's all, your job is over. That is the translation. Coming to the rotation, you have to rotate the coordinate system such that origins are coinciding. Because recently you studied the rigid body dynamics and rotation. So whenever you want to rotate, you have to fix the point, and that point is the origin. Origin has to coincide. That is important. And coming to the moving coordinate system, whenever something is moving, the question will come about velocity. So let us say that the velocity may be constant, the velocity may not be constant. So I'll write down that it may be constant or it may not be constant. velocity, I mean to say velocity may not be constant. Non-constant means non-uniform, so non-uniform speed. So now you have all these things, and we will call this as the Galilean transformation. So Galilean transformation refers to a generic name. So I will write down that. I will better write down that the terminology for all this set is the Galilean transformation. And we will see how many parameters are involved in total Galilean transformation. Okay. So if you want to perform the Galilean transformation, how many parameters or what are the variables required? That we will see now. Starting to the translation, we need 3 parameters. That is easy to understand, right? I can move in x direction, I can move in y direction, I can move in z direction. So mathematically we can write down like x0, y0, z0. What is that suffix 0 means? Some constant. x0 means constant. You can say that I am moving the coordinate by 2 meters. I am moving the coordinate by 3 meters in the y direction. That is what I mean to say. That is the simplest situation. Coming to the rotation, similarly you have 3 angles. We can give any symbol, but okay, we can give something like we can give theta, phi and psi. And typically the names are known as Euler angles. So Euler angle means 3 angles which are measured with respect to the x-axis, y-axis, z-axis respectively. Okay, that's all about it. Euler angle means that is the one. So once you understand that, now you can count how many, you just count how many parameters are there. So already we have a 3 plus 3, right? 3 plus 3 is there. Now what about the moving coordinate? See, we didn't write down there, so let me write down that now. Coming to the moving coordinate system, how many parameters are required? I need 3 more parameters are required. What are they? What is the velocity in x direction? Vx, Vy. What is the velocity in Vz direction? Vz. That's all. 3 more are required. So now that you have all the total, now you simply add them. I will now show where are they. 3 parameters for the translation, 3 angles for the rotation, and 3 parameters for velocity. So 3 plus 3 plus 3. So therefore, after making the counting 3 plus 3 plus 3, I will write down the conclusion. What is the conclusion that I would like to write is that we have a total is 9 parameters are required for the time being. And then you also have one more, I will write down that plus one more for the time translation. Because time translation is too simple, but for the purpose of completeness, we have to write down. Okay, we have one time translation means what? Simply shifting the time. Shifting the time. So as an example, how do you understand shifting of time? It is very simple. It is like, start the experiment at 9 a.m. I can say that you are starting the experiment at 9 a.m. You can ask the question, why should I start at 9 a.m.? Why not 10 a.m.? So like that you can ask, then you say that, okay, start the experiment at 10 a.m. So shifting the time from 9 a.m. to 10 a.m., that is called the time translation. So for that, how many parameters are required? 1 parameter. So now you have 9 plus 1. So therefore, what is the total? That is the, that we will make it as a conclusion. So after this study, what is the main conclusion is, I will write it down as a conclusion that the Galilean group is a 10 parameter group. That is what is the conclusion. The Galilean group. Okay, group is a technical term. Okay, right now we are not going into the axioms of the group theory, but however, under the group theory, this set of 10 parameters is forming a group. That means it is satisfying the axiom. So that is the meaning of this. But however, what is our interest is that under this influence, we are studying the properties of invariance of the physical laws. So we are interested in the invariance of the physical laws. That is very important. That is our interest. Okay, we are not going to study the group theory now. Our interest is, okay, there is a group, Galilean group is there, 10 parameters are there. Now the question is whether physical laws are invariant or not. That is our interest. So therefore, I will highlight what is the conclusion. The highlight is the Galilean group is a 10 parameter group. That much is the highlight. I mean, the highlight means there is a conclusion. But however, our interest is on the invariance of the physical laws. So I will put some kind of underlining. So we are going to study something. So what are we going to study? Is that we are going to study the physical laws. So I will underline that we are going to study the invariance of the physical laws. What are the physical laws that we are going to study means which physical laws? This should be clear to you. Which physical laws are we going to study? So the answer that we will see, and we are asking the question, okay, you studied all this thing, what is your conclusion? That is the question. So what is the conclusion of your study? What I mean is, we are interested in the question, finally, are the physical laws are invariant or not? I am trying to explain the meaning of conclusion of study. Conclusion of study means, are the physical laws invariant or not? That is what is our interest in relativity. Fine. So let us now answer this question. Which physical laws are we going to study? The answer is the first one. Okay, let me finish this and come. Okay, the first one I will put A. The first one I will put the A is the Newton's laws, because that is the you started with the Galilean's transformation, and the second one would be the Maxwell's equation that gave the troubles. So Newton's laws are fine, so we are not at all having any trouble with that. But Maxwell's electromagnetic equations gave trouble. So I will write that information in the right hand side. So I will split the board into two parts so that the confusion will not be there. Now you see what is the question on the right hand side. Are the physical laws invariant or not? That's the question. What is the answer? The answer is a long answer, but I don't want to wait for a long time, so I want to see the answer quickly. So in that case, I can write like this. The point number A is Newton's laws, we are happy, so I will say yes. So for Newton's laws, the conclusion is, or we say that yes, they are invariant under Galilean transformation. Under Galilean, GT means Galilean transformation. But the problem came with the B, namely the Maxwell's equation. So I will write down that Maxwell's electromagnetic equation. EM means electromagnetic. I will write it as EM equations. No, the answer is no. So I will say that they are not invariant under the Galilean transformation. So this is the short answer. That means without explaining any mathematical foundation, simply I am telling that okay, Newton's laws are invariant, Maxwell's laws are not invariant. But if I tell like this, there is no way to appreciate and learn something. Therefore, we need some mathematical workout. We have to do some mathematical workout. So that's what we are going to do. So now I will put the important point. So this is the starting point for the development of relativity. So now you understand why should we read relativity at all when the Galilean transformation was there much earlier. So that the trouble came, right? The trouble comes from the Maxwell's electromagnetic equation, and that is the sparkle that gave rise to the fire. Okay, so this is the starting point. Now to understand better, this is a short answer. What is the long answer? To get the long answer, we will have to do some mathematics. So I will write down that we will prove this. We will prove this first. That means Newton's law is first, right? Maxwell equation is second. That's what I mean. First means that's what I mean. Newton's law. After finishing the Newton's law, we will come to the Maxwell equation, and then I will say that okay, we will prove this one later. Later means what? Later means after that. Next I will write. So now you understand that quickly we got the answer for the time being, but however, for the purpose of clear understanding and then have a mathematical way of working out things, we have to do this kind of proof. So let us do that. I think the board is full. I will move to some other place. I have to move to a different place in the board. So our objective is clear, right? Let us start the Newton's equation and then apply some kind of rotation of the coordinate and then check whether the invariance is there or not. That is the idea. That is the first plan, our plan. So first of all, let me go to a different place in the board. Okay, and then okay, so let me write down the title. What is that we are planning to do? We are planning to study the invariance under rotation of the coordinate axis. So objective should be clear, otherwise you don't know what we are doing. So we have a coordinate system and we want to rotate. That's all about it. So let me therefore draw a coordinate system. I have to draw an x-axis horizontally and then y-axis y-axis vertically. Okay, that's what I'm trying to do. So x-axis and y-axis we have, of course, 90 degrees there between x and y-axis. Now I want to rotate this by some angle. So I will plot it in some kind of yellow color. Okay, so I want to rotate slightly, let us say something like 10 degree, 20 degree, something like that. So the rotation will be looking like this. So after rotation, it is x prime and y prime. This is after rotation. X prime, y prime, and then the angle of rotation, you consider it some angle, okay, theta we can write down. That is the angle of rotation when compared to the original. So if this angle is theta, y-axis also same angle should be there. You can't have different one. Because x and y-axis are 90 degree, right? That condition is there. Because of that reason, both angles must be theta only. And then the original axis will be labeled by x and y. That's all about it. And then you have a common origin that is always there. And let us consider any point in space. I'll put it in green color. Let it be any point in the space. So how do you represent any point in space? X comma y comma z. But that is also equivalent to x prime comma y prime comma z prime. So that is clear. So once any point is there, now I want to draw a line from the origin to the point. So draw a line from the origin to any point. In green color I am planning to draw, and we will call this as the r vector. So r vector is only for symbolic representation. So r doesn't mean position vector, etc. It can represent any physical quantity. So I will write down that the green color line that I have drawn could represent any physical quantity such as force, momentum, electric field, whatever it is, any vector quantity. That's all I mean to say. So this is clear, configuration is clear. And what is our question? Our question is, just because I rotated the coordinate system by an angle theta, what happens to the vector? What happens to the study of the vector? I mean, we are going to study the vector, right? What will happen to that? Will anything happen? Or the original vector all will be retained? That is the question. So we will address that issue now. The point to be noted is that we are going to rotate, right? So therefore rotation is about the origin. Because how did you rotate? You have to explain. So I am rotating it about the origin. Not only that, but with the z-axis as the axis of rotation. If you don't tell axis of rotation, then it is a big chaos. So you have to tell the axis of rotation. In my diagram or in our diagram, it is the z-axis is the axis of rotation. So that will give you the clarity. If this is not there, then some information will be missing. That's why I am writing. Okay, this is over. Now what is our objective? Our objective is what is the relation between, we are asking the question, what is the relation between the rotated coordinates with the original coordinates? So I will write down that the relation between rotated coordinates with the original coordinate system. Coordinate system, I will write it down as CS. Okay, that will be given by, of course, this is given by a rotation matrix. You'll have to recall rotation matrix that you studied in. I think it is there all the way from school. Rotation matrix is generally introduced in school, and therefore you have some idea about the rotation matrix. And therefore I'll now write down what is the connection, that x prime, y prime, and then z prime. That is given by the standard rotation matrix in 2D. So remember 2D. I'll write down as cos theta minus sin theta, then sin theta, then cos theta. That is for the 2D. Then what happens is the third, you said the 3D is there, right? What about z-axis? For z-axis is not entering into picture. Therefore, I will write it down in the green color and I will say 1. I'll explain the meaning of 1. Let me finish the equation. Close the bracket. I want to close the bracket first. Then multiplied by the original coordinate xyz. So this is the relation. That means the old coordinate xyz is related to the rotated coordinate x prime, y prime, z prime by this matrix multiplication. Now come to the 1. What do you mean by the green color 1 that I have written? This means that the z-axis is the invariant. Z prime equal to z. We did not rotate the z-axis because it is an axis of coordinates. So rotated coordinates is, I will underline the rotated coordinates and I will explain it at the end. Rotated coordinate I am underlining in the green color. I just want to tell that rotated is different from rotating. Okay, rotated coordinate is different from rotating coordinate. That point I will tell later, but now let us proceed further. So this matrix equation can be written down in the index notation. I will write down this. In the index notation, how the above equation will look like. We can write easily like this. There is an x prime, let us say. So we can say that it is xi, then you say prime will be equal to capital R can be a matrix, then you can write ij as the 2 indices and then you have an xj. And you have to tell what is the range for ij, that means 1, 2, 3. So this is the index notation. If you are not happy with the index notation, you can use the traditional vector rotation with the arrow on top of it. Okay, most of the people are comfortable with putting vector, right? So if you want to write in the traditional notation how it looks like, that also I will write down so that things will be clear. So in the traditional vector notation, what happens to R vector? R vector goes to means what? Under rotation. Goes to R prime under rotation. That is the meaning. You have to read like this. R vector goes to R prime vector. Which means that R prime vector is equal to capital R multiplied by the R vector. That is the meaning. So I will put a box and say that this is the main result. This is important result. So our conclusion is this, that the vectors are column vectors. Otherwise, matrix multiplication will give you trouble. So the vectors should be written down in the column style. Then only the 3 by 3 matrix can come into picture. Okay, since R is a 3 by 3 matrix, I am emphasizing this point. So let us put a box and say that this is equation number 1. The conclusion should be clear, right? Rotated coordinate R axis, that is the R prime vector, is equal to R times this. So it is only a pure multiplication of matrix. Okay, so these two are same actually. Whether you write it in the index notation or you write it in the vector notation, both are same. And now what is our interest is that let us take the Newton's law. Okay, so after putting equation 1, let us go to the Newton's law. So now we will apply equation number 1 to which equation? Newton's second law. Of course, second law is the only equation that is appearing in the equation form. Therefore, we will write down that F equal to ma. What will happen to F equal to ma? F equal to ma goes to under rotation. Like that you have to read. So under rotation, F equal to ma goes to what shall I write here? That's what I am thinking. You can write F prime. Do you agree? So how it F prime you can write, you can see, or if you want one more step, you can write down. So what is that one more step? If you don't want F prime, you can write one more intermediate step. What is that? You go back and check. F is there. F is written like this. But so this is the first step, going to the R prime. But R prime is, what is R prime? R times R. So R going to R prime is R times R. So F going to ME means now what you have to write? You have to write R times F. So in the same style you have to write down R times F. Right hand side it becomes F into F. M is a constant, forget about it. A goes to R times A. A goes to R times A. Now Now using this symbol, now you can write down f prime equal to m times a prime. How did you write prime? Means using equation 1, because using equation 1 on the left hand side is the prime notation, and that's all. So this is the conclusion. So what is the conclusion now? Our conclusion is the appearance of the Newton's law is retained. Appearance means form. The appearance of the Newton's law, okay, I will write simply law, okay, is retained as original. That means whatever was the original appearance, F equal to ma, same appearance is there now also. That is the important point. That is called invariance. Okay, this is called invariance. I'll put some kind of blue color circle. So you have to compare with the before. This is the before transformation, before rotation. After rotation, this is the after rotation. Before rotation is inside blue color. After rotation is inside the rectangular white color box. So if you compare them, their appearance is retained as original. If this happens, okay, if this happens, then we can say. So I'll write down that. Then we can say that the Newton's law is invariant under rotation. So now you understand the technical meaning of invariant. Invariant means the original appearance of the equation is retained as such. So that is the highlight, or that is the main conclusion. So when it happened because of rotation. So under rotation, that is very important. So okay, so our conclusion is fine. So I will write down one note here, because I have put some green color underlining. So let me write down about the rotated coordinate system. Rotated coordinate system is not the same as rotating coordinate system. I just want to tell this because last 2 classes or something like that, we were studying rotating coordinate system. So these two are not same. Rotating means continuously rotating. Rotated means you slightly rotate and then stop it. That is the difference. So rotated coordinate system means it is a stationary coordinate system. Just I want to mention this point, that's all. Which means that there is no continuous rotation. Okay, there is no continuous rotation and there is no motion. I mean translation motion. Nothing is there. That's all. So this is the point to be noted. Now let us come back to our original discussion. That is the short answer. In the short answer, what did we say? We said that Newton's laws are invariant. And now it is visible. So Newton's laws is invariant under GT. We will prove this like that I said. So at least you are now happy that one part of the proof is given now. So you now know how to work with some kind of rotation transformation and then prove that it is invariant. But that is not complete. It's only one part. Why it is one part means only rotation you did. What about the velocity transformation? Isn't it? We didn't discuss about velocity transformation. Velocity transformation means what? Moving coordinate system. For moving coordinate system, we did not discuss anything about the invariance. So I think that we can do it in the next class. I'll write down that. Probably that we will do in the next class.